Okay, so thank you guys for filling out the survey. I had a couple different ways we could go with the next couple of lectures. One of them was to continue on the more details about RL, but it seems like there was more interest in other areas than RL. So I'm going to jump ahead a little bit, talk about the intuitive physics portion, which I think is, we didn't even ask you about that one because I think it's important enough that I wanted to include it. And it does connect to RL. You could call this, you could think of this as maybe part of the model-based reinforcement learning pipeline. And let me just kind of transition from the RL and behavior cloning kind of conversation into what we're going to talk about today. So we talked about, I've been saying over and over again that I like visual motor policies, right? And so far, where the goal of the visual motor policies is to control the state of the world and the robot. And so far, we've given you two major pipelines to possibly try to find those visual motor policies. The first one was behavior cloning. And the second one was a very brief look at a big topic of reinforcement learning. And both of those can work. Both of them, I mean, all of the approaches we'll talk about have strengths and weaknesses. Actually, there was a really interesting question that came up at the end last time. I guess the person who asked it isn't here yet today, but someone asked if I had just run RL for longer on the box flip up, would it have done something less ridiculous, right? And I answered quickly, and I think I answered about how RL can get stuck in local minima, and maybe because it's stochastic enough, it could jump out and eventually find its way down. But I think there might have been I don't know if there was a deeper point to that question, but it occurred to me that, when people like David Silver talks about RL for Go, for instance, he gives the impression that, I think there's a belief there that the more you learn, the better you'll get at Go. That you've got enough parameters in your network, you've got enough experience coming in that you can just, it's just the amount of compute you're willing to spend, it'll just get better and better and better the more you play. And so I don't think that's the regime we're in with the RL examples I've been showing you here. I can't say that, this is my intuition and my, experience, but maybe not a proof here. But I don't think we're in that regime with the robotics RL experiments that we've been seeing in the field yet. I think we're more in the regime where you can bounce around, but you can really get stuck in local minima. And one of the reasons might be that we're not really in the dramatically over-parameterized regime in the policies, where we can just keep going down and down and down and down. Okay, but RL is doing a pretty good job of, even without a model, finding its way into at least a local minima in the cost landscape. And if you run it long enough, it might bounce around to a better local minima, but it's not guaranteed to solve the global problem in any way. Okay, so how are we going to go from, why are we going to move on from this to something about learning models instead, right? So the drawbacks of both of these approaches, I think, are largely about generalization. So the experience we talked about in supervised learning was this amazing capability of transfer learning, that you can learn on ImageNet and apply that to some different domain. I think a strong criticism of reinforcement learning and behavior cloning is that these tend to be very task specific. Okay, so if you have a particular task, you want to flip up the box in a particular way, you write your cost function, you find your policy, and this is a strength and a weakness actually of this, is that it learns exactly the policy it needs to learn to accomplish that task, and it doesn't learn other stuff. And that gives it power by ignoring all the things it doesn't need to learn, but it's also a limitation if you want to then change the task a little bit. The naive recipe is you just start over, right? There are ways to try to make RL generalize more. You can talk about goal-conditioned policies, for instance. Where maybe you make, if you can find an efficient way to parameterize the objective function, the goal, let's say, then you could basically throw that in your state space. It's not quite that, but imagine putting it into your state space. Okay, and then learn a policy that is a function of the goal parameters as well as the state. And there's also nice work on sort of multitask RL, which is, I think, a very powerful framework. And I think that field's still growing up, but these, this is going to be a constant struggle because, like I say, it's a good thing about RL that it ignores all the things that are not relevant to the current task at hand. So that's one of its strengths. But if you want to compare that to, for instance, our kinematic trajectory optimization or something, where you give it a new task and you just change the cost function on the fly, you're doing the new task, right? RL is not doing that. It's not immediately well suited to that. It's a very, you do a lot of computation to get a good controller for one cost function. And you have to start over. So the most sound way, I guess, to address that is to learn something more than just the parameters of the policy. You want to learn something that generalizes from different task to different task. And the opposite extreme of that is that maybe what you should do is actually learn the dynamics, right? I talked about these things are hard because we don't know what the dynamics of spreading peanut butter on toast is, or what the dynamics of buttoning my shirt are. But neural networks are pretty good at learning things. So why don't we try to learn the dynamics of the world and then apply our best control tools to those learned dynamics? Okay. So the idea for today is try to learn the dynamics of the world. Some versions of this will actually just try to learn the state representation. In addition, some of them will require you to give a state representation. Okay. Now, some people call this model-based reinforcement learning. I'm not a huge fan of that particular word, just because people do model-free reinforcement learning, even though they have a simulator, which is a model in my book, and this one could just be called control, but it's called model-based RL. Don't get hung up on the naming, but I guess if you want to call it model-based RL, yeah, you're welcome to. Okay, so let's talk today about learning the dynamics of the world and what tools do we have to offer about that. It's a super rich subject, and actually, even once you learn the dynamics, model-based control, of course, is a huge subject, and that's one that I spend basically all of the underactuated lectures talking about how to do model-based control. But let's think about, today about learning the dynamics and what kind of tools we can bring to bear on that. And there's sort of a zoo of model parameterizations that we might try to learn. Right, we talked about a little bit about it, but broadly speaking, learning dynamics is the topic of system identification. Let me say AKA system identification. Or at least that's the old word for it. And even though I think there's a lot of things from system identification that we want to remember, I think there's also a lot of new tools for machine learning that have come and recently contributed, new life to some of the old system ID questions. And that's not just deep learning, that's also finite sample results and online optimization kind of results that are very, very powerful new approaches to system identification. Okay, but in the world of system identification or learning the dynamics, the first thing we have to do is we have to pick a family of models that we're going to optimize over to try to explain the data, right? So the standard thing is I have some system coming in, or some data coming in, let's say, some signal coming in, I'll call it. I have some system that I'm trying to fit, and I have some signal coming out. These are my actions and my observations in this case, right? And we've already talked about some of the different forms that this could take because we used this sort of setup for even learning policies, right? So we said already that you could talk about static parameterizations, which would be yn is just a function of un. We've talked about feed forward or Rmax kind of models, where we could say that my output is some function of my previous outputs. un minus 1. And we've talked about state space models. Right, so I might learn something where this is the x of my controller. Right, so we've talked a little bit about that before, and I won't talk about it again. But now the question is, given that we're going to choose one of these forms, whether it's a static or a feed forward or a state space kind of model, I want to start digging into what are our choices for f, and what are our choices for g if we have one, right? And what parameterizations can we say strong things about, and what can we, what gives us. There's going to be pros and cons to each different choice of f and g. Okay, again, there's lots of choices, and I think I can kind of paint the picture, and then we'll dig deep into one or two of them. Okay, so you could choose f and g to be linear. That's a natural, powerful choice, really, because it affords so much analysis that we can understand a lot of things through the lens of linear dynamics. Even theoretical machine learning folks had a few years where they returned in force to linear dynamical systems to understand finite sample bounds and everything like that. The other case that we can really throw the math hammer at would be if you did finite models or tabular models. If you're thinking about stochastic versions of this would be like learning the traditional MDP Markov decision process. Those two, I think, have limits to what they can represent, but they have huge value in what we can understand through those lenses. So a lot of times, some of the lessons that you learn in linear control are pretty specific to linear systems, but some of them generalize beautifully, and we should take those lessons and carry them with us, because it's much harder to see the same lessons in the more nonlinear setting. Okay, of course we have neural nets. But in the world of neural nets, there's all kinds of choices, right? We have even, okay, in any one of them there's a lot, but there's the standard sort of feed-forward neural networks, ConvNets, and all the others. We talked about recurrent networks like LSTMs. But what you'll see more and more in some of these model learning cases, you'll see graph neural networks come up. Transformers are coming. They haven't been a huge focus, but they're coming, right? I think. And so on, right? All of these are going to be relevant, and we'll give a few examples maybe in the next lecture on this. But then there's also, I think, different levels at which these try to represent the world. Some of them operate directly on pixels. Some of them try to operate on particles. They try to say that I'm going to assume the world is based on particles or almost point clouds. Some of them try to do more object-centric kind of model. This is the broad strokes, and I'll go into a few examples of these. Now, it's interesting to put these right next to each other, right? Because linear and tabular have limits on what they can represent, but they have huge, powerful backends mathematically. Neural nets can represent anything, but we have less that we can understand when they're not working well, and less guarantees about if you care about proving your robot's not going to do something bad, let's say, and they're going to also be harder to control with, harder to do control design for. There are many other nonlinear models, model parameterizations. I don't know if you've heard Volterra series, or you can learn polynomials, you can learn all these different things, okay? And I put a few of them in the notes, but I won't dwell on them now. Neural nets have consumed people's attention on the nonlinear model front. But the one that I think I don't want to forget about and I want to spend some time on today is the multibody equations, which is a particular type of nonlinear models that has the important structure of Lagrangian mechanics, okay? It's far richer than these models and what it can represent. And there's another important consideration too, right? So if you're just doing system identification for the sake of system identification, then maybe the only metric is to try to predict as well as possible y given u. Okay, that's the standard system identification metric. But if your goal is to do system identification in the service of building a controller and getting closed loop performance, then that can change your requirements a little bit. It might be that, for instance, actually you don't have to predict all of your observations perfectly. Some of them are task relevant, some of them are not task relevant. But there's also, it could, if I learned a perfect predictive model of my system, but with equations that are very hard to do control design with, then that's a problem too, right? So I think one of the interesting things, I'm sorry to pan on you here, but one of the interesting things here is that, if I were to learn a model that could describe the data that was linear or tabular, then control design is easy. If I learn a model that's a neural network, depending on how big or complicated the neural network is, then it might be that control is still hard, okay? The multibody equations are somewhere in the middle, right? There's a lot of structure in those equations. If you can find the multibody equations that describe the data well, then we have more structured tools, more powerful tools for control, okay? And there's some things we know about this that just are so strong and so powerful, and I want to make sure people remember about them. Okay, so let me start by digging in a bit to learning multibody equations. And I'll do it by I'll motivate it with throwing stuff, yeah? So, Oops, I don't know the audio. So a bunch of people watched the Tossing Bot video. Everybody in the CIM class in the first lectures talked about the Tossing Bot paper. This is the video that went along with that paper. Great paper by Andy Zhang and company of picking up relatively, basically unknown objects and tossing them into a target location, right? Now they used a neural network to do that. Well, they used a combination of a simple model, and then they learned a residual neural network to capture the differences. So I think a lot of people have seen that, and I won't play the whole video here. It's a nice long video, beautifully put together. But there was an original Tossing Bot that I don't think as many people have seen. Okay, this is actually work from MIT, but in like 91, okay? All right, so this is a WAM robot, a Barrett whole arm manipulator. Okay, let me just show you what it does first. Okay, but again, what it's doing is actually, so now that the bin is right here, which is about the size of the ball. It's a pretty small bin, by the way, right? You saw I did a little regrasp there just to know where it is. Right in the bin across the room, okay? The mass of the ball was unknown. The size of the ball was unknown. It was approximately what fits in the hand or whatever, but there was something even more remarkable about that. There wasn't learning in that. This was online system identification and adaptive control, okay? So let's just watch it one more time here. That was too fast. He's throwing to a person, by the way. Human-robot interaction. Okay, so watch what happens here. Quick regrasp, okay? Now right here, there's one back motion and one forward motion. And what you don't realize is that in that backward swing, it's estimating the mass of the ball. And then, then it computes exactly what it needs to do to throw it into the target wherever it is. Really good, okay? They went on and did other versions of this too. They actually didn't publish the ball throwing one. This is Jean-Jacques Slotin's work. And actually, when I first came to the AI lab, I only got here much later, but the arm was still up in the 9th floor of NE43. It was at the time. The way they tracked this, they had cameras up here. Let's see if I can turn the volume off again. They have cameras up here, and they're doing foveating vision. Okay, so there's a bright red ball or a bright white ball in the last one, and they just get the cameras to lock on the initial location of the ball, and then they track the white blob. This is before computer vision really worked, right? They track the white blob with the servoed cameras, and they could back out the 3D position of the ball based on that, the center of the ball.
So they know where the prism is in the last time?
That's a good question.
Maybe just throw back and track.
Probably, yeah. This is catching paper airplanes, okay, with a simple model of a paper airplane. So this one, the catching one doesn't involve the same parameter estimation. They did some online tracking, and they have incredibly good control, which I'll mention at the end, of trying to align. They're using feed-forward inverse dynamics, model cancellation, but it's also an adaptive control, and they take into account the mass of the ball when they're executing their trajectory. Okay, but this is pretty good. 91, like catching airplanes out of the air, throwing balls across the room into targets exactly the size of the ball. It's pretty good. Okay. So let's think about how they learned the model of that, and how the sort of rich initial literature on learning the dynamics of the objects in the world. And it goes through multi-body equations. So let's just even think for a second about what you need to know about the ball in order to be able to do a good throw. The dynamics of throwing are nice because they're simple if we ignore aerodynamics, okay? So you could throw anything. You could throw a banana, that's an example from Andy. It sounded arbitrary, but it was the last thing I saw them throw in the tossing by video when I just played it. You could throw a banana, you could throw a ball, you could throw whatever. Any one of them, no matter how complicated, they might flip around or whatever. If you write the dynamics of the center of mass, then it's trivial, okay? The dynamics of the center of mass are always, if I just do it in the plane, if I do the center of mass, without drag, the dynamics of the center of mass are simple, depending if I put the g as positive or negative, right? And even the rotations around the center of mass there's an conservation of angular momentum. This is the moment of inertia about the center of mass. It may spin. It may be spinning around the center of mass, but it won't spin more or less as it flies through the air because of conservation of angular momentum. Okay? So there's a couple things that immediately we can notice here is that this implies that since mass is not zero, that x double dot center of mass is 0, z double dot center of mass is negative g, and theta double dot center of mass equals 0. And in the air, you don't have to do any work to estimate the parameters of the mass. The mass of the ball is irrelevant once you throw it, right? Similarly, if you were to throw a ball at me, there's no way that I can, just by watching the motion of the ball, I mean, this is classic physics, that I could estimate its mass, right? Every ball will take the same arc. Just remember that. So now, why then do we have to estimate, why is it useful to estimate the mass of the ball if we're going to throw it? Well, what matters very much is the location of the center of mass and the spatial velocity of the center of mass at the point of release, right? So everything follows from that. There's no accelerations after you launch. But if you don't know where the center of mass is when you launch, then you've got no hope of controlling where it goes, okay? So what matters is the moment of release. This was all in the air. It has nothing to do with the moment of inertia. That's just a bad choice of words, maybe. But so I care about the spatial velocity in general. The position and spatial velocity. At release. Okay, so at very least, when I start moving around, I need to know the center of mass of the ball or of the whatever banana I'm going to throw relative to my hand. Okay, so that's the key parameter to estimate. And then depending on how heavy the banana is relative to your arm, you might also need to know the mass and other things just to be able to execute the trajectory well enough, right? If the object is insignificant mass relative to your arm, then your robot controller can just ignore the mass and execute its trajectory and expect to do well. But if you start to throw heavy bananas, I got to pick a different object, then suddenly the ability to track a trajectory with very high fidelity, I mean, that's high fidelity to throw it in the bin all the way across, right? With very high fidelity requires you to consider the mass in the hand. And that's where the extra terms from mass and inertia start coming in more, is in the tracking. And it's a good problem for lots of our applications, right? Is we want to Amazon wants to move boxes fast, or you want to play tiddlywinks, or whatever your robot wants to do. There's a lot of applications where you'd want to be able to pick up an object and learn something about its inertial properties by interaction. Okay, so let's just think about how would we learn those parameters by picking up an object and moving it around. Turns out that estimating the mass of an object in the hand, especially once it's in a reasonable grasp inside the hand. Remember, they opened and closed to make sure they had a really good grasp, and it was solidly at the base of the gripper. It turns out that's just a special case of the more general problem of estimating mass and inertia of your robot as you move around, okay? Okay, so how do we do multi-body parameter estimation? What does that even look like? How do we set it up? What special structure can we exploit? What guarantees do we think we can get? Right, so the multi-body equations, you've seen me write them many times. They might have other terms like friction, damping, contact, you name it. Other terms like that. These are nonlinear equations, right? You'll see sines and cosines inside this. So that sounds like we're going to have a tough nonlinear estimation problem. But it turns out the parameters that we care to estimate enter these equations in very particular ways, okay? There's parameters inside here, right? In all of these, possibly in those two. And they tend to be of two basic varieties. There's the kinematic parameters. Lengths, for instance. And then there's the dynamic parameters, like the masses and the moment of inertias. Okay? You can actually estimate them jointly. That's okay. But, just get a ruler for this one. If you don't have, like this one, you should probably just measure fairly well. And then there's actually there's more subtle problems in kinematic calibration, which are more about joint offsets, if you have like an encoder offset error or something like this. But a lot of times people will separate out the kinematic parameter estimation and maybe have a way to, so a lot of our robots actually wake up and go against the joint limits and then come back just to sort of calibrate their joint encoders. And the lengths are normally pretty faithful to the CAD models. So I'll talk about estimating them jointly because we can, but know that I wouldn't actually recommend that. You should probably just pull those out and estimate them separately. You could, for instance, just try to draw a straight line, and if it's not a straight line, you haven't got your kinematic parameters working very well. Okay, so what's the special structure? They enter here into these different terms. Hidden inside there are the masses, the inertias that make the equations of motion, and they're nonlinear. Yeah? You can estimate some of the parameters of friction. There are identifiability requirements. So for instance, if I never see it slide, I'm not going to be able to get its friction coefficient. But yes, the rules of the game apply to friction as well. More subtle. Okay, so if you take away exactly one thing from this part, you should know that there is a very important particular way that those parameters enter the equations. And it's true of basically the same way we said almost every kinematic chain is representable as a polynomial. Basically, almost every multi-body set of equations that you'll come across, the parameters enter in a particular way. And it turns out that the worst nonlinearities, your sines and cosines or whatever, are separable from your parameters. That your parameters group together and your sines and cosines and other nonlinearities group together, and you can separate those two apart and estimate just the parameters, and it's a nicer problem than you would expect out of the box. And I'll show you that in a simple example. The simplest of possible example is just the one link robot, which I think is the right place to write it on the board, and then I'll show a couple more complicated examples. So if I just make my pendulum dynamics, and I have my mass and my length and my gravity coming down and my theta, then the equations of motion, ml squared theta double dot. Maybe I have some damping. Okay, so in this particular set of equations, which I know by heart, you can see that what I said is true, that these things are separable. If you know the lengths already, because you did separate kinematic trajectory kinematic parameter estimation, then that gets even simpler, okay? But even if you don't, it's useful to write the equations in a slightly different form. Let me separate out the what I would consider to be the data. That's the things we're getting from our measurements and our sensors, and I'll throw the sign on that. From our parameters, I'll just write it in a vector form here. And that thing equals tau. Okay, in general it's a scalar as I've written it here, but in general it can be a vector. Okay? Yes? Oh yeah, thank you. ml squared. Tau is also measured. Yeah, so here we have data coming in, which will have in general the trajectory of theta and tau. Yeah, and we can take its derivatives. Okay, so we're going to have all those come in, and we can just compute this a priori. There's no parameters involved, and this is our parameter vector. In fact, this is famously known as the lumped parameters. Now you might say, well, that's not cool. I've got a mass here, I've got a mass here, it entered twice. I want to make sure I estimate the mass. There's some coupling I haven't acknowledged in that. That's true, but it turns out that these are exactly the parameters you need to know to do prediction. You can't know more than that. We'll say that more carefully in a minute. You can't sort of know more than that without some other priors on those things. And this is actually, I think, maybe the right way to think about the parameters. The way we happen to write it in the URDF doesn't line up perfectly with what you can estimate in the real world. Okay, so that's just a different way to write those equations. If I write them over the course of an entire experiment where I have lots of samples of this and this over time, right? I have the entire trajectory. Then in general, I can write the equations. I can write my system, my parameter estimation problem in terms of a data matrix, which would be, let's call this thing W. where I'll write all of my w's these are at time equals 0, let's say. I'll do the same thing at time equals 1, right? So theta at time equals 1, theta dot, this is just all of my data, and I'll stack them up into this. Okay, I've got the same parameter vector. And now I have the torques at T0, T1, okay, so if you're willing to give me that this is an okay vector to try to estimate, and certainly if I do estimate this, then if you give me a new state of the robot, I can predict the torques, and if you can, I can do all the operations I want if you give me the value of that vector correctly. I can evaluate the dynamics. Okay, then you can see from this that solving for the best lumped parameters is actually just a least squares problem. So that's a very specific, even though they're nonlinear equations, we can actually solve for the lumped parameters with least squares. Okay, so that's super important idea. It turns out it's more general than pendulums, right? It works for the general multi-body equations. You can take any equations of this form that come out of our multi-bodies, that when these things are derived from multi-body equations, then you can basically, I think screw joints might screw this one up too. But like I said, just don't use screw joints in your robot. That screws up all of our math, okay? In general, I can have this big data matrix times my parameter vector is my other side of my data matrix, right? So this is just my right-hand side here, whatever the leftover stuff is. I can convert this set of equations into this, and even when they're more complicated, I've got the double pendulum equations here, oops, right here. Okay, that's the double pendulum equations. It still turns out that even though m, c, and tau are more complicated, the little c2 is my shorthand for cosine of theta 2, right? Sines are s's, okay, but the point is that they still separate out. I get a sine of 1 plus 2 is sine of cosine of theta 1 plus theta 2. So you get lots of instances that look like parameters times sine of, let's say, theta 1 plus theta 2, whatever. But what we're saying is what you don't get, and what's beautiful is you never see, for instance, a sine of m theta 1 or anything like this. None of my parameters sneak inside my ugly nonlinearities. So it's more structured than the general set of grab bag of similarly nonlinear equations. Right? I don't see a length that ever pops inside there. It's only all those nonlinearities operate directly on the angles. And so it's separable. But wait, there's more. So I can solve for the fact that I can solve for the lumped parameters with least squares means I can do even more, okay? So it turns out that not all parameters are identifiable, and this goes to Tom's question about friction and the like, okay? So there are some parameters that you might have written in your URDF, which get turned into your multi-body equations, that you won't be able to estimate. Let me give you an example, right? So if I'm a Iwa bolted to a table, I wrote down in my URDF the inertia of that link 0. But no matter how much I move around the Iwa, I've got no data that could possibly, the inertia of the bottom link has zero effect on my dynamics. It's been welded to the world. So I will not be able to estimate that. And on the flip side, it has nothing to do with, I don't need to estimate it because it has nothing to do with my dynamics. Okay, if you go up one link, now there's only a one revolute joint before the first link. So you can move that thing around, but you're only going to ever estimate the moment of inertia about the one axis that moves. There's two other axes of a moment of inertia that will not be relevant to your dynamics, right? It's just, it will affect your mass, you know, like you could, but the inertia around those other axes is unidentifiable. So what's beautiful is because we're in the realm of linear algebra, we can see that. How does that manifest itself in these kind of equations is that the data matrix will drop rank. There will be some parameters here. If they are not identifiable, then the data matrix will have a zero singular value corresponding with those parameters. And in fact, before you even start, you can do basic analysis to extract the identifiable lumped parameters. Okay? I'll just say with linear algebra, right? So the point is we're in the space of linear algebra here, and all of the concepts of rank and singular, kernel of that matrix and stuff apply, okay? And it's a direct operations on the data matrix, which we've separated out. Again, that's not a bad, having a low rank data matrix does not mean you're a bad person, right? It just means that there are some parameters that are irrelevant to the dynamics. So you will not be able to estimate them, but you also don't need to estimate them. There are some deep implications of that, right? So like I said, if you throw a ball at me, I'm not going to be able to test to know the mass of the ball before it gets to me, right? If I've watched a ball fall and then I go to pick it up, I can't, from just passive observations, know the mass of the ball. In fact, as a general rule, one of the things you see from the identifiability is you're going to need force measurements or to apply actions in order to estimate any mass kind of parameters, right? I could watch a video of a walking robot, and I have no concept from just watching a video whether it's a 40-foot tall, car-crushing, fire-breathing, massive robot or like a little walking toy, right? Unless there's something else in the background that gives me context and I use common sense. But from the motions of the robot, the joint angles, I won't be able to tell. Okay, so robots probably can't learn everything by watching YouTube, right? Some of us want that to be true, but you're not going to learn inertia from watching YouTube. It's not identifiable. Okay, so that's cool. Or yeah. At some point, robots matter. You have to have embodiment to learn everything about the world. Even riffing on that even just a little bit more. In all learning kind of applications, there's a question of data generation, of exploration, of experiment design. Okay, so if the robot we watched in the video just went like this, and that was enough in that particular case to estimate the parameter it needed to throw the ball. But in general, just going like that won't be enough to estimate the parameters that matter for your EWA, if you wanted to estimate all those parameters. And there's a nice problem of experiment design. Okay, so let's say your goal is to design a trajectory for the robot to follow that will excite the parameters so that the system identification problem goes well, right? Because we're in the land of linear algebra, there's a natural objective for that. you can just look at the condition number of the data matrix, and you'd like to say, I want to get as much of the parameters to have data, to be away from singularity as possible. You don't expect to get all of them. Some of them are unidentifiable, but the ones that are identifiable, you'd like to move their singular values away from 0. Okay? So there's a natural trajectory optimization formulation. It's a little bit ugly to implement, but people do it. This is, is that you design up to your torque limits and maybe don't drive your motor crazy, right? You put some heuristics on costs on action, but then you put a cost on the condition number of the data matrix to design informative trajectories for parameter estimation. Okay? Okay, so let's just pause for a second and just think. I motivated this conversation by saying, I think there's going to be cases where you want to train a neural network to do a lot of these tasks. The things you're training the neural network are multi-body systems in most cases, for in this class, yeah. Even if you want the representational power of the neural net, a lot of these lessons about what's identifiable, how do you excite the parameters, what do you expect to estimate, what do you not expect to estimate, still apply. In particular, the thing that I said is linear in the lumped parameters is this equation. This is not the dynamics of the robot. This is the inverse dynamics of the robot. If I were to take mass matrix inverse to solve for the forward dynamics, then things get worse. Right? All of my parameters become rational in my parameters. I don't get these beautiful polynomials. I get mixtures of the sines and cosines in ways that are in the denominator and the like. Okay, things get worse. But basically every machine learning project that's learning dynamics is learning the forward dynamics. I think there's room to explore that more. Okay, and there's a lot more lessons, and I'll try to point them out as we hit them. Okay. But this idea of doing nice experiment design and having a metric that talks about how well you can identify the parameters, that's a luxury. We don't have that in the general case, but it's a beautiful way to have it in this case. Okay, so let me tell you how you'd actually do this, right? So in the particular case of the pendulum, or maybe the double pendulum, the lumped parameters come in a way that it's I can fit it on a paper. If I do a little scratching on the paper, I can extract the lumped parameters. I could write a program to estimate them. You don't want to do that for the EWA. The equations don't fit on a page. They're big and ugly. They have a structured form. So there are actually specific numerical recipes that will extract the lumped parameters directly. The same way you'd write a recursive algorithm to generate the equations of motion, you can write recursive algorithms to extract lumped parameters. They're a little bespoke, and actually I think not many people have implemented them. You can get them in Drake using the symbolic toolbox. Right? I'm actually very proud of this. This is a lot of people think I'm crazy for have emphasized symbolic as much as we did. But here's the reason why it's very powerful. Okay. Well, I'll just show you in code. Right? I'll make it a lot bigger than that. Okay, so I'll just do a very simple example here, which is I'll take the double pendulum. I'll load it into my multi-body plant. I'll make some symbolic variables for Q, V, and dot V. Okay, and then the parameters that I want to estimate are going to be the mass and the length in that particular one. I could have put actually I put a to do to make the damping in. And I can, in order to put that into the manipulator equations, I have to compute the spatial inertia in terms of the mass, just to relate the mass and length to the operations. I do a little work with spatial algebra, and then I just basically ask the symbolic engine to print the equations of motion, and it'll give me nice little LaTeX equations of motion through the dynamics engine, right? So that's, you guys know, probably understand kind of how it's built behind the scenes, but behind the scenes in Drake, we build all of our systems, or almost all of our systems. They'll support doubles, they support autodiff, and they support symbolic, okay? And any system that opts into supporting symbolic, you can just ask it for its symbolic equations, and it'll generate them like this, okay? And I can get all of them like that. Okay, so let's do a simple example then. So the cart pole is a very, it happens I did it on the cart pole instead of the double pendulum, but it's another two-link system. It's a common one in control. It's in the AI gym. Okay, let's just do the lump parameters for the cart pole and do some basic estimation. And I'll just show you how the mechanics of that works, right? So this, I know the equations look like this, but I'm not going to use them directly. I'm going to use the multi-body engine to get them. The first thing I did is just generate a bunch of data. Okay, so I loaded in the multi-body plant. I loaded the cart pole URDF. I made a trajectory to input. I didn't do the optimal experiment design on this. I could have, but I just did something much simpler, which is I made a sine wave. Okay, because the cart pole, there's kind of only one thing you can do, right? You've got only one motor and one passive joint. So all I did was I just shook the motor back and forth for a little bit, made sure it was sufficiently exciting, parametrically exciting. If I chose that to be too large, things might have gone crazy and it wouldn't have a condition. If it was too small, then it wouldn't excite the dynamics. Well, I'd have a low condition number. Okay? So I just generate a bunch of data, and what's important to me is if I plot, I just rolled it out 4 times, reset it to 0, rolled it out 4 times, and I got what I considered to be, so the sine wave, the period of the sine wave was a function of the rollout. I did slightly different sine waves on each sweep, and I was happy to see that X moved more than a little, but not too much. 0 to 4 is like a pretty sweet, 4 meters is like a good amount of data. Okay, theta seemed in a reasonable regime, and in fact, I will check the condition number and show that it's reasonable. Okay. Now I'll estimate the lumped parameters, and I'll do the symbolic thing to get the lumped parameters, and then I'll fit them with least squares. So I'm going to pretend I didn't know about that multi-body plant, come up with a new multi-body plant, load it again, make the symbolic version of that, make my decision variables, or those are my data variables, and then my parameters that I'm going to fit is the mass of the cart, the mass of the pole, the length of the pole, just because I can, even though I should have just gotten a ruler. Okay? And then I'm going to fix the input to be the data and evaluate the dynamics. Okay, and I basically generate my big data matrix, which I'll show you how it comes in here. I just get a big matrix. I called it W0 instead of Y here. Okay, and then I just call NP linear least squares to extract the lump parameters. And then I have my fit parameters, alpha. I called the vector alpha. I have my true known parameters alpha, which came from the URDF. And the question is, how well do I do? And I actually don't know why it's random. Why is it random? I've noted that it's random. I don't remember why. Okay, but I get my symbolic acceleration residuals are this, but my lumped parameters, so the URDF says the lumped parameters, the joint mass of the cart pole should be 11. I got 10.91. If I did a little more data, I'd get better. You know, my mass times the length is 0.5, I get 0.56. And this is a case where more data does make it better. Yeah, that's just me being a little lazy, not letting it run for very long. Okay, so that's really powerful. I think people should know about that tool chain, right? If you want to estimate the parameters of an object, and you assume that the object is welded, you need some model of how it's connected to the hand, and some measurement of how it's connected to the hand, because you need, like, if you said it was connected to the hand in a pin joint, then you would need the angle theta of that pin joint to feed into this algorithm. The standard thing is to make a grasp on the object and assume it's welded to the hand. Then you estimate the inertia of the hand as well as the object. And you can do that with just the joint torque sensors. You can do it better if you have a force sensor in the wrist. Okay? You run, the nice thing is that, so symbolic computations get expensive as you do lots of symbols through lots of nonlinear equations, but you only have to do the symbols that you're trying to estimate, and the rest it treats as doubles. So you just make the parameters of the system symbolic in the unknown parameters of the inertia. You run your experiments, you back it out, and you have an estimate of the inertia. You can actually do a more special case, more dialed in for if it's exactly just one inertia you want at the end. In fact, there's an even more specialized version of that. But the recipe is this. It's just a special case of that. Any questions on that? Yeah.
If for some reason, instead of, okay, sorry. So you had said, like, if there are too many parameters, then, like, we lose rank. If you ever have a situation where, like, it's kind of under constrained, like maybe there's, like, some joint you didn't think of or something like that, does that manifest as, like, a poor fit, or what does that look like?
So it's a great question, and let me repeat it. So the question is, what about, so I talked about cases where there are unidentifiable parameters. What happens in the case where there are, I think the case you're talking about is really the case where there's not enough data to excite the, I mean, the opposite version of having losing rank would be if you don't have enough data in your matrix to identify all those parameters. You could similarly, in that case, you would expect to get more data and be able to bring the rank up and identify. You said, okay, the other extreme you're talking about is if there's, if you're over constrained, you would expect that if your lumped parameters came from the equations of motion, then there is a solution that satisfies all of those. So the having insufficient data, insufficient rank is one thing, but you wouldn't expect to be in an over-constrained situation if if those lumped parameters came out of the inertia, the equations of motion. I think that would be the natural other side of the linear, of the over-constrained equations instead of under-constrained. Was that your question?
I think so. It's kind of like, let's say I was, like, swinging an object around, but the object, like, had a hinge on it.
Yes.
And so it was affecting
I see.
my measurements.
And I didn't tell my equations about that. What would it do? So it would find so the question is, if I didn't declare in my equation the fact that the object is sliding in my hand, what would it do? It's going to find the least squares approximation given the data for the rigid leaf. I mean, for whatever model you fit. So if you said it's rigid and you have accelerations that are inconsistent with that, it'll try to find the best explanation given the model you fit. That's one of the beautiful things about the least squares, is that you actually expect to get the best model in the class, but it can't guarantee if your model class is wrong, it won't, of course, overcome that. Yeah, so I think it will do it relatively. It doesn't die catastrophically in that sense, right? It should try to find the best in class. Other questions like that? Yeah.
I guess on the other hand, like similar, but like if you didn't know whether you were holding a rigid object or a pendulum or a double pendulum,
Yes.
then like you wouldn't be able to apply this to that case. You would need to somehow figure out which one it is, and then you could apply it.
Yes. Good. Right. If you there's a question of sort of estimating the numbers of degrees of freedom in the object that you're trying to manipulate, and that is an extra interesting question where you're actually trying to do Well, so there's ways that you could do that through this lens. You could try to fit the one-dimensional version, the two-dimensional version, the three-dimensional version, and expect to find some amount of, of any more degrees of freedom will only explain it better, but you would expect, same with like proper orthogonal decomposition or PCA or anything like this, you'd probably expect the fit to level off when you found the appropriate degrees of freedom.
I guess the difference would be like you need your cues in order to estimate.
That's right.
You don't have single electrical theory, you don't have cues of
Good. Yeah, good point. Yeah. So in that case, so we have assumed that you have the cues. You could do it. No, you're right. You're right. That would be the sticking point, is we wouldn't have cues in that setting. Mm-hmm. Yeah, people do a lot of work on topology estimation and the like first, and it's typically a pre-processing step, a separate optimization. Nice. Okay, so there's a lot of other hidden lessons here. So there is actually one thing that when I was talking about the overparameterization, it kind of came to mind. It is possible that in some sense we have overparameterized our URDF, okay? When I said that, I kind of caught myself. So there is one sense in which we are overparameterizing our URDF, which is that if we specify the mass and the center of mass and the 6 numbers of the inertia matrix all separately, then you have actually overspecified the number of free parameters. And it is important, if you want to get a dynamically consistent inertial matrix out, then you actually have to put in a few additional, they can be written as convex constraints. A pretty tight approximation of what it means to be a valid inertial matrix can be written as a convex constraint. But that was, just as I said that, I was like, I should be a little more careful. Okay, so yeah, our URDFs are not a minimal representation of the parameters, right? And in fact, it's kind of the one case where you might want to go back and back out mass separate from length, separate from whatever, is if you want to write your results back into your URDF to share with your friends. Then you would have to solve that last piece of the problem, but it shouldn't matter which ones you pick in terms of the simulation. If you had an initial guess, you could solve a nonlinear problem saying, give me the closest to the initial guess in some least squares sense that satisfies exactly the lumped parameter values. That would be a standard thing to do. I looked for a while at whether you could do that convexly, and I don't think you can. Only in very simple cases can you. Okay, so just to finish the story for the throwing, it turns out that because this is least squares, it's beautiful, it's good, you can actually do it with recursive least squares online as you operate. And that's what's happening in the Slotine throwing example, is that he's actually estimating the parameters of the ball as the robot's operating. And then there's a desired trajectory, but the execution of that desired trajectory is using a computed torque inverse dynamics controller that has the adaptive parameters in. So it's actually refining its execution of the trajectory as it throws. So it really does estimate the mass of the ball and then throw it better because of that estimate. Awesome, right? And you remember in the inverse dynamics setting, we talked about error could go to 0 if you put the feed-forward term in. There are the famous result by Jean-Jacques at Slotine is that you can still get that in the parameter estimation regime. You can still get your tracking error to go to 0, even if you have to estimate online some of your parameters because of this least squares result. That's a very strong result. It requires, it does require your system to be fully actuated. It requires that you have a controller that can accomplish the task stably without any parameter knowledge. And basically it just gets better and better as the parameters dial in. But it's a famous classic result.
Basically updating the model using the controller, but the controller is a fixed closed form.
The controller is a closed form function of the parameters. The parameters evolve along with the state of the robot. This is an adaptive controller architecture. So you think of having my dynamics for Q, but you also have your dynamics for your parameters which are the recursive least squares estimator, typically. There's a couple other more clever ways to do it where you can estimate a subset of the parameters in order, but the simplest way to think about it is a recursive least squares, update to the parameters, and a controller that's using those parameters to execute the trajectory. In that line of work, sorry, you guys got me talking, which is great. But in that line of work, they also did some residual models. You know, the residual models back in the day were radial basis functions or radial basis functions. They did a couple other, they did a lot of wavelets actually back in the day. I'm sure there was a neural network version of it, but not a deep neural network version of it, right? And they worked incredibly well, and that's how they fit the airplane, I believe, was with a radial basis function network. So I think residual models can be added on top of this, and actually a radial basis network with fixed means would still be linear in the parameters. So it fits beautifully in this kind of framework. If you compare that to the tossing bot is solving a harder version of the problem because it is worrying about unknown center of masses and rotations that are more complicated than what Jean-Jacques did. It's potentially talking about aerodynamics. The paper talks about aerodynamics. There was at least one ping pong ball that might have been subject to aerodynamics, right? So it is solving a harder version of the problem. If I had one wish for that paper, would be that it would compare it against the fully adaptive controller, because there was an intermediate result that would have been really nice to say how much does the neural network residual learn over the parameter adaptive controller. Okay. One last maybe nugget on that. So let me just write it on the board since I said it in that conversation, but an interesting lesson is all the nice properties are for the inverse dynamics. The forward dynamics is less pretty. And there's one other, I think the algorithms that people tend to implement are not quite what I said. There's another nice insight, which is that we talk about how Q, V, V dot are the data that I talked about. We've said so far that these two are relatively clean data. I've said it's okay to use those in your controller, but be a little careful sending your raw acceleration measurements back into the controller. This is a little more noisy. Maybe be more careful. There's a version of the same sort of parameter estimation story where you can reduce the sensitivity on the accelerations by writing basically the error in terms of power instead of in terms of torque. And that allows you to average out over some time some of the noise in the acceleration. So there are power formulations or even energy formulations. Can decrease sensitivity. To V dot. Pretty good. I think that stuff's very, very powerful. Maybe underappreciated. I won't do all of linear control in 5 minutes, linear system ID in 5 minutes, but maybe there's at least one thing one lesson I would say from linear system ID that is immediately applicable to this. And so I'll just say that one idea and we'll wrap up for today. There's loads of insights different insights from linear system identification. But one of them is this. Different people have different names for it, but there's a distinction between equation error versus simulation error. Okay, so if I have my system identification problem, there's maybe even, let's just pretend I have state observations just to keep it simple. There's sort of two ways to write the objective of system identification, two common ways. One of them is the equation error is the one-step version. Which is I'm going to minimize over my parameters alpha the dynamics of alpha of the one-step dynamics let me get my notation careful here. So I'll use a lowercase like this. Okay, so this would be, I'm trying to use this is my data, okay? When I use the subscript here, I'll say that's data that's coming in a priori, whereas this is a simulation of my model. I'll write them both, and I think it'll be clear what I'm trying to say. Okay. Sorry, that was a lot of writing. There's two ways you can write a system identification objective. One would be to say, all I want for my model is that every data point, I'm going to reset my simulator to the current data point. I'm going to take one step, and I'm going to compare it to the data at the next step. That's a different objective than if I say I'm going to take my simulator, I'm going to put them in the same initial condition, I'm going to simulate forward using the parameters alpha, and I'm going to have my data, and I'm going to then evaluate, even in the long term in the future, the long-term rollouts. Right? The question is, am I going to reset on every time step, or am I going to roll it out with the dynamics? The multi-body parameter estimation that we just did was this version, where we reset the data on every step, and we only implemented the dynamics for one step. And that's for a fundamental reason, which is this tends to be, even in linear system identification, this tends to be the easier objective. It's convex in the multi-body case, and the multiple step one is non-convex. Okay? This tends to be the better objective for an important reason. The simplest argument I can give you for that is that you can find models that minimize the equation error, which actually have unbounded simulation error. And the particular case that comes on, like a simple way to sort of think about that is if you have a model you're trying to identify that's on the boundary of being stable, that the true model is actually stable, okay? You could find a set of parameters that fits in the least squares sense, but actually gives you an unstable model, okay? So your true data is stable, it maybe goes towards 0, it happens even in the linear setting, okay? Your least squares fit because you didn't have perfect measurements, or you got something, your best estimate came up with an unstable model and they diverge. That doesn't happen if you can minimize this error, but this model is susceptible of it. So even in the multi-body setting, we tend to use least squares and do our very best with that. But oftentimes we do a cleanup pass. This looks like a trajectory optimization problem, finding the parameters alpha that satisfy over an entire rollout. We will often fine-tune alpha at the end after the initial solution here, just to make sure we minimize the long-term error. Okay, and this is in the linear system identification world, there are strong approaches to actually making this problem still good. Okay, and there's lots of lessons there too, but I won't jam them in at the end here. Okay, but I do want you to understand that there's a difference between a one-step and a long-term, and the long-term is the one we really want. The one-step is the one we often use because it's more convenient. Okay, to be continued. Happy Thanksgiving.